Imagine trying to figure out the shape of a giant underground rock formation that's miles beneath your feet. It's filled with oil or gas, but you can't see it, you can't touch it, so how in the world do you map it? Well, today we're diving into the incredibly clever ways engineers turn simple pressure data into a detailed picture of this huge hidden world.
Think about it like this. If you were suddenly in a pitch black room, what's the first thing you'd do? You might shout, right? And you'd listen for the echoes. How long it takes for that echo to come back tells you how far away a wall is. A nice, sharp echo probably means a hard, solid wall, but a muffled, faint sound, that might be an open door. Reservoir engineers use this exact same idea, but instead of sound, they're listening to pressure.
So that gets us to the core idea here, the echo and the mirror. Every time a well starts producing, it pulls fluid out and sends a pressure wave through the reservoir, kind of like a ripple in a pond. When that wave hits a boundary, say a solid wall of rock, it reflects back. The whole trick is figuring out how to read that reflection, that echo, to understand what kind of boundary it is and exactly where it is. The way engineers pull this off is with a brilliant mathematical tool called the method of images. And the heart of this method is something called the image well. Now, this isn't a real well. It's a virtual one, like a mathematical ghost that we pretend exists on the other side of the boundary. This virtual well perfectly mimics the pressure effect of the real boundary, acting just like a mirror for our pressure signal.
Okay, so let's walk through how this actually works. First, our real well starts producing. That's our shout into the darkness. That pressure wave travels out until it smacks into a geological boundary, our wall. Then the math creates that virtual image well on the other side of the wall. What we measure back at our real well is the combined effect of our own production and the reflection from that virtual well. And by analyzing that combined signal, we can start to map the wall.
Now, just like in our darkroom, not all boundaries are created equal. A solid rock wall that just completely blocks any flow is going to create a very different pressure echo than a boundary that leads to, say, a huge open aquifer. So how can you possibly tell the difference between a dead end and an open door? Well, it turns out there are two fundamental types. First, you've got a ceiling fault, which is basically a dead end. To model this, our virtual mirror becomes another producing well. Its pressure drop adds to ours, which makes the combined signal much, much stronger, a loud, clear echo. On the flip side, you have a constant pressure boundary. Think of this as an open door to a massive water source. To model this, the virtual mirror becomes an injecting well. It pushes back and cancels out our pressure drop, which pretty much silences the echo. And this shows the signature of a ceiling fault perfectly. Engineers use a tool called the pressure derivative. You can think of it as a way of cranking up the volume on these echoes to make them easier to see. Before the wave hits that fault, the signal has a certain strength. We'll just call it 1x. But once the echo from that image-producing well arrives, the signal strength exactly doubles to 2x. So when you see the signal double like that, you know you hit a solid wall. And the signature for an opening, that constant pressure boundary? Well, it's the complete opposite. Because that virtual image-injecting well is canceling out the pressure drop. The signal doesn't get stronger, it just fades away. The derivative dives straight down towards zero. It's the exact same thing as shouting and hearing nothing back because the sound just went right out an open door. Okay, so identifying a single wall or an opening is one thing. But let's be real, reservoirs are rarely that simple. What happens when you're stuck in a corner with two or even more walls all meeting up? The echoes start to get a whole lot more complicated.
Let's take that classic case. Your well is producing, and it's boxed in by two ceiling faults that meet at a perfect 90-degree angle. What do you think happens to our pressure signal now?
4 times. The signal quadruples. It jumps by a factor of 4. And why? Because you don't just have one echo anymore. You have the echo from the first wall, the echo from the second wall, and you even have an echo of an echo bouncing off the corner itself. All those virtual image wells add up, and they create this massive signal that tells you, without a doubt, that you are in a 90-degree corner. And what's amazing is that there's this really elegant mathematical rule for this. It's called the 360 over theta rule. The total jump in your signal is simply 360 divided by the angle between the faults. So for our 90-degree corner, 360 divided by 90, that's 4. If the angle was 60 degrees, the jump would be 6x. This little rule lets engineers calculate the angle of a corner they will never, ever be able to see. It's incredible. All right, so we can map corners. But what if you're not in a corner at all? What if instead you find yourself trapped between two parallel walls, like you're in a long, skinny riverbed or a channel? The pressure behavior, you guessed it, changes all over again. So let's follow the signal's journey here. At first, the pressure wave just expands outwards in a circle. That's called radial flow. But pretty soon, it hits both of those parallel walls. It can't go sideways anymore. The flow gets squeezed, and it's forced to travel straight down the channel. This is a totally different pattern called linear flow. And this linear flow has its own unique fingerprint. Instead of leveling off at a higher value like it does for a corner, the pressure derivative starts rising steadily with a very specific half-unit slope. When an engineer sees that on their plot, they know. They just know they're sitting inside a channel. It's another crucial piece of the puzzle for building our invisible map. So, we've learned to identify walls, openings, corners, and channels, all from their unique pressure signatures. But why go through all this trouble? Why does this invisible map actually matter? It matters a lot, because this map drives decisions worth millions, sometimes hundreds of millions of dollars. Knowing the reservoir's shape helps companies figure out the best place to drill their next expensive well. It lets them accurately calculate how much oil or gas is actually down there. It helps them avoid making a costly mistake, like drilling into a tiny dead-end pocket. Basically, this map lets them create a smart, strategic plan for the entire life of the field. I absolutely love this quote because it just perfectly captures what this work is all about. The raw data isn't just a bunch of numbers on a screen. The pressure response is a story. It's a message sent up from miles underground, and it's written by the geology itself. The entire goal of this whole analysis is to become fluent in that language, to learn how to read the story that the reservoir is trying to tell us. And that really leaves you with a bigger thought, doesn't it? This whole method, using waves and their reflections to map out an unseen space, it's just so powerful. It makes you wonder, what other invisible worlds are out there? You know, from the inside of the human body to the distant corners of the universe, that we could start to map if only we knew how to listen for the right kinds of signals.